What if I told you that the invisible highways your data travels on are constantly being reshaped, divided, and secured, all to ensure your apps run smoothly and your information stays safe? It's a silent architectural marvel happening every second, allowing billions of devices to communicate without chaos. From the cloud to your coffee maker, everything is connected and it all starts with data communications. Before we deep dive further, if you find this discussion valuable, please take a moment to like, subscribe, and share this deep dive with others. You won't want to miss our insider tips that could help position you for a bright future in your chosen careers. And remember, for additional resources that can jumpstart your journey, check the description below. Today, we're unraveling the intricate world of network segmentation. Think of it as the art and science of carving up a larger, sprawling network into smaller, more manageable, and crucially, more secure segments. This isn't just, a technical exercise. It's a foundational strategy that underpins nearly every digital interaction you have, from the simplest online search to the most complex corporate data transfer.
And for all you BCIS 1347 and 3347 students at Tarleton State University's Dr. Sam Pack College of Business, this deep dive is specifically designed to complement your studies. We're drawing directly from Chapter 8 of the CompTIA Network Plus Guide to Networks by Jill West, 10th edition, 2025. This material is absolutely core to grasping data communications technologies, the hardware and software that make them tick, the protocols that govern them, and the critical managerial considerations that shape how businesses implement these solutions. It's all about helping you identify effective communication solutions and understand their current and future impact.
Right. Our mission today isn't just to demystify complex terms. We want to bring these concepts to life with real-world examples, highlight their strategic business value, and equip you with practical insights directly applicable to your career growth. We'll show you why understanding network segmentation isn't just academic, it's essential for navigating our increasingly connected and, well, often vulnerable world. Okay, let's unpack this. Why do we even bother segmenting networks? From a business perspective, isn't it just adding complexity to what seems like a perfectly good single big network? It feels like we're creating more work.
Yeah, that's a good question. You're hitting on a crucial point about perceived complexity versus actual benefit. At first glance, it might seem counterintuitive, right? But segmentation is fundamentally about gaining control, boosting efficiency, and drastically enhancing security. Think of it like a thriving city. You don't build one giant open-plan office building where every single person has access to every floor, every department, every sensitive file cabinet. Instead, you design distinct buildings, maybe secure floors, access-controlled offices for different teams. Networking is really no different. It's about intelligently organizing your digital real estate.
Okay, like city planning for data.
Exactly. And the core benefits become really clear once you see past the initial setup. The ultimate insight into segmentation security. It's basically your digital firewall, or maybe more like internal bulkheads on a ship. It's designed to prevent a single point of failure from becoming an organizational catastrophe. By dividing your network into segments, you can create very specific access policies. These are enforced by your network devices, things like routers and switches. This prevents unauthorized access between different groups of users or, say, sensitive systems. If one segment, let's imagine the guest Wi-Fi, gets compromised.
Right. Happens all the time.
The attacker doesn't immediately have free reign over the entire corporate network. It's like quarantining a patient to prevent a widespread outbreak. Containment.
So it's about containing a breach, which is a massive business benefit. Huge. What about performance, though? Does all this dividing actually make things faster? Or is it more like building extra walls that just slow things down?
Good point. It absolutely makes things faster and more efficient. That's the second major benefit. Improved performance. See, in a traditional large, flat network, meaning no segments, every device on a switch receives every single broadcast message.
Even if it doesn't need it.
Even if it doesn't need it. That's a lot of unnecessary chatter or traffic that can really bog things down. By segmenting, you drastically reduce the size of these broadcast domains. Imagine a single, perpetually congested highway. Now imagine dividing that highway into smaller dedicated lanes, or even separate, shorter highways for different types of traffic. Fewer cars on a smaller dedicated lane allows for faster, more predictable traffic flow.
Okay, so my important servers aren't getting stuck in traffic caused by, I don't know, printers broadcasting.
Precisely. Your high-performance servers aren't wasting cycles, processing broadcasts meant for the guest Wi-Fi, for instance. It keeps things running smoothly.
And when something inevitably breaks, which, let's be honest, it always does.
Something always breaks.
I assume this makes fixing it easier.
That's exactly right. That leads to the third major benefit, simplified troubleshooting. When a problem arises, maybe a slow connection or a device offline, you can isolate the issue to a much smaller, more contained network segment. Instead of sifting through thousands of devices on a huge network, you can quickly narrow down the problem. Maybe it's just the accounting department segment, or just the third floor.
So faster diagnosis, faster fix.
Quicker identification and resolution of network issues, absolutely, which minimizes costly downtime. And for a business, every minute of network outage is a tangible hit to productivity, sometimes even revenue. This skill, by the way, is directly tied to that learning outcome about identifying network architecture for troubleshooting. Understanding the segments is key.
That makes incredible business sense. Okay, so when we talk about dividing these networks, how do organizations typically group things together? Are there common patterns or, best practices?
Oh, absolutely. Networks are commonly segmented based on logical groupings that align with business operations or security needs. Very logical, usually. For instance, geographic locations are a natural fit. You might separate traffic for different floors of a building, or even different buildings on a sprawling campus. Makes sense, right?
Yeah, physical separation.
Then there are departmental boundaries, which are very, very common. HR, finance, engineering, sales. Each of these departments often has unique security and access requirements. So making them their own segments is ideal. This ensures that, say, sensitive financial data stays within the finance department's segment, completely inaccessible to, say, the sales team, without explicit authorization through a router or a firewall.
Layering the security.
Layering, exactly. We also see segmentation by device types. Dedicated segments for printers, servers, IP phones, or guest devices are crucial. Imagine guest Wi-Fi being on the same logical segment as your production database servers. That's a security nightmare waiting to happen. Isolating these prevents a guest's potentially compromised laptop from affecting critical business operations. This directly contributes to selecting appropriate networking components and, of course, configuring security properly.
Beyond the everyday office environment, I've heard about specialized segmentation for things like operational technology and storage area networks. For a business student, what are the unique risks and strategic reasons behind segmenting these? They sound critical.
They are incredibly critical, and this is a huge area, especially with the increasing convergence of IT and industrial systems. Operational technology, or OT, along with the Industrial Internet of Things, IoT, refers to the hardware and software that directly interact with physical infrastructure. Think of SCADA systems monitoring HVAC across a city, traffic signals managing flow, or even the critical controls for mass transit systems.
Stuff that really can't fail.
Stuff that really cannot fail. Traditionally, these systems were often air-gapped, meaning completely isolated, physically separate from IT networks. But with the IoT, connecting these OT systems to the internet promises huge efficiencies, like remote monitoring and predictive maintenance. The problem is, it introduces significant cybersecurity risks.
Because now they're reachable.
Precisely. And here's the strategic insight you need to grasp. Unlike a typical data breach, which, while bad, might be costly in terms of data loss or reputation, a breach in OT can have catastrophic physical consequences. Think power grids going down, manufacturing lines grinding to a halt, water treatment plants malfunctioning, or public transit systems being disrupted.
Okay, yeah, that's way beyond data loss.
Way beyond. This makes the segmentation of OT not just important for data security, but for physical safety, environmental protection, and fundamental operational continuity. The solution involves robust logical segmentation into zones. You might have an untrusted zone, like the internet, a trusted zone, your core OT, and a screened zone, like a DMZ in between, creating layers of security. Sometimes guest and voice zones, too. It's a vital aspect of formulating a risk assessment and developing appropriate security strategies for any modern enterprise dealing with physical infrastructure.
That sounds like a whole different level of risk assessment compared to just, say, protecting customer emails. And what about storage area networks, or SANs? That sounds like a specialized solution for massive data needs.
Indeed. While smaller businesses might use network-attached storage, or NAS, which employs file-sharing protocols like CIFS or SMB for Windows, or NFS for Linux, that's usually for basic server storage consolidation, file sharing. It works at the file level. Large enterprises, however, have vastly different needs. For these organizations, requiring incredibly fast access to massive amounts of data, a storage area network, or SAN, is often essential. SANs are specialized, high-speed networks designed specifically for block-level data access. Think raw disk blocks, not files. This contrasts sharply with NAS's file-level access.
So faster, more direct access to the data.
Much faster, and designed for high transaction volumes. From a business perspective, the benefits are substantial. SANs are highly scalable, offering massive storage capabilities that can grow as the business's data demands explode. They boast very high fault tolerance. This means data remains available even if multiple components fail, which is absolutely crucial for business continuity and disaster recovery, especially in environments hosting huge numbers of virtual machines, VMs, that constantly demand quick data retrieval.
What kind of tech makes that happen?
Technologies like fiber channel, FC,
Right.
which is very high speed FCOE, fiber channel over Ethernet,
Mm-hmm.
ISCSI, Internet SCSI, which runs over standard Ethernet, and InfiniBand, IB, are the backbone of these high-performance, fault-tolerant storage solutions. Understanding these alternative transmission facilities is key for selecting the right components for any given requirement, especially in large-scale deployments.
So getting a handle on these telecommunications and data communications fundamentals, how they apply to different transmission media, different network infrastructure, it's really key here. It allows you, as a business or IT professional, to identify where data flows, how it can be segmented effectively, and therefore where vulnerabilities might lie. It enables you to build a resilient and secure network. This foundational knowledge is crucial for designing robust logical networks and developing effective security strategies.
Absolutely. It's the bedrock.
Now, let's dive into the nuts and bolts of how this segmentation actually works. This next concept, subnets, is often where people feel they hit a bit of a wall with the technical details, but it's truly powerful once demystified. It sounds a bit like complicated math to me.
You're right. It can seem that way. And there is some math involved, no getting around it. But what's fascinating here is that subnets, or subnetworks, operate at layer 3 of the OSI model. That's the network layer. This is where IP addresses live. And subnets are essentially how we logically divide a large pool of IP addresses into smaller, more manageable groups. While it does involve some binary calculations, the core idea is quite intuitive, really. Once you grasp it, it becomes a powerful tool for network design and management.
Okay, break it down for us. What is a subnet at its core?
At its heart, a subnet is simply a smaller network inside a larger network. It's a defined group of IP addresses. The critical role of routers comes into play here. Routers define the boundaries between these subnets. Each interface, each connection point on a router effectively creates a new broadcast domain, acting as a separator.
So routers are the gatekeepers between subnets.
Exactly. And this is crucial for network efficiency. Subnetting ensures that network traffic takes the shortest, most efficient path to its destination within your network. Think of it like a highly organized postal service again. When you send a letter, the Postal Service sorts mail by local post office for quicker, more direct delivery, right? It doesn't send every single letter through one massive central hub for sorting. Subnets do something similar for network traffic.
Okay, so it's about efficient routing and less congestion, less unnecessary traffic bouncing around. From a business management perspective, what are the direct benefits of using subnets effectively? Why should a manager care about this?
For a business, the benefits are quite clear and tangible. Well-chosen subnets make network documentation much easier to manage because you have clearly defined address ranges for different segments like floor 1, floor 2, server room, etc. Problems become easier to locate and resolve because you can often isolate them to a specific subnet, which improves troubleshooting efficiency dramatically. Less guesswork.
Faster fixes again.
Faster fixes, less downtime. Routers can also more easily manage IP address spaces that don't overlap. And on larger networks, routing becomes significantly more efficient when IP address spaces are mathematically related at a binary level. The router can summarize routes more effectively. It's really about bringing order to what could otherwise be IP address chaos.
So tell us about IP addresses and how they fit in.
Right. Every device on the internet, or any IP network, needs a unique IP address. For example, an IPv4 address looks like 203.1 over 0.113.110s. Critically, every IP address has two parts: a network ID, which identifies the network it belongs to, and a host ID, which identifies the specific device within that network. Historically, with IPv4, we had this thing called classful addressing, class A, B, and C networks. The length of the network ID was fixed based on the class. Class A networks could connect millions of devices, Class B fewer, and Class C fewer still. It was quite rigid.
And the subnet mask, what's its job in all this?
Good question. The subnet mask's role is to work internally within your network. It's used by routers and computers to figure out which part of an IP address is the network ID and which part is the host ID. Most importantly for segmentation, it helps sort data into specific subnetworks. It's not something that's transmitted across the internet, it's an internal organizational tool. Imagine you're a network manager in a company that just acquired another firm. If both companies were using the same internal IP ranges, like 192.168.1 dot something, you'd have a massive conflict. Subnet masks are how you logically carve out distinct sections, distinct subnets, even if they physically share some infrastructure, allowing devices to communicate correctly.
And that's where CIDR notation comes in, right? The familiar number you often see, like 24 or 16.
Correct. CIDR, classless interdomain routing notation, is a shorthand, like 24, that tells us precisely how many bits of the IP address are dedicated to the network portion. In binary, a 24 corresponds to the decimal subnet mask, 255.255.255.0. This means the first 24 bits of the mask are all ones, indicating the network portion, followed by euros for the host portion. This flexible method replaced the rigid classful system, allowing for much more efficient use of IP address space, which is a major cost-saving and efficiency gain for businesses, especially with IPv4 addresses being so scarce now.
Okay, the calculations. For our learners, especially those new to networking, the actual calculation part of subnetting can feel like a really steep climb. Can you give us the core conceptual understanding and maybe some key takeaways for how to approach it without getting totally bogged down in every binary detail right now?
Absolutely, and you're right, it does take practice. While a full step-by-step calculation is best followed along with a visual aid or a chart, the core idea is to identify the working octet, the part of the IP address, the subnet mask effects, and then use powers of 2 to quickly map out your network ranges. The goal isn't just to do the math, but to understand what the math accomplishes, creating those logical boundaries for your network segments, defining the size and scope of each subnet.
Okay, so working octet and powers of 2, how does that work?
Right. The first step is usually to determine your working octet based on the CIDR mask. For example, if you have a 28 mask that's between 24 and 32, you know you'll be working primarily in the last or fourth octet of the IP address. Then you use powers of 2 to find your block size, or sometimes called the hop size for your subnets. How big is each chunk? For a 28 mask, you calculate 32 total bits in IPv4 minus 28 network bits equals 4 host bits. Then 2 to the power of that result, 24 is 16. This means your subnets will increment by 16 in that working octet. So if you start at 192.168.4.0, your subnets will be 192.168.0 to 1028, 192.168.1628, 192.168.4.3228, and so on up to 0.240.
And finding the usable addresses within those blocks.
It's exactly. What's critical for a network professional, and this comes up constantly in real-world tasks and certification exams, is being able to quickly identify the key addresses for any given subnet. The network ID, the first address, like 0.0.16 in our example, you can't assign this to a device. The broadcast ID, the last address, like 0.15 or 0.31, also not assignable, used to send messages to all devices in that specific subnet. And the range of valid host addresses in between, for example, 0.1 to 0.14 for the first subnet, 0.17 to 0.30 for the second. This skill is absolutely vital for network design, for configuring network connections correctly, and for troubleshooting when things go wrong. We'll include a detailed, printable guide to this method in our show notes for you to practice. But the core skill is about quickly defining those logical boundaries for your segments.
That helps make it much more conceptual, less about just the raw binary. Okay, so once we have these subnets defined, how do devices actually get their IP addresses within them, especially if we have multiple subnets scattered across a building? Do we need a DHCP server in every single subnet?
That's a great practical question. That brings us to DHCP assignments across subnets. DHCP servers, or Dynamic Host Configuration Protocol servers, are responsible for automatically assigning IP addresses and other configuration details, like gateway address, DNS servers, to devices. To serve multiple subnets without placing a DHCP server in each one, which would be inefficient, they use mechanisms like UDP forwarding. This is often configured on routers using features called relay agents or setting up IP helper addresses. These essentially listen for DHCP requests broadcast within a subnet, then forward those requests unicast directly to a DHCP server located on a different subnet. The server then sends the reply back via the relay agent. This ensures all devices across multiple segments can receive their necessary network configuration efficiently from a central server or servers.
Centralized management, nice. Now, you mentioned IPv4 addresses are scarce. How does that impact subnetting strategy?
That scarcity really drives the need for VLSM, or variable length subnet mask. The key insight here is about conservation and efficiency. Standard subnetting uses the same size mask for every subnet, which can be wasteful. VLSM allows us to take a subnet and further subdivide it into even smaller, more appropriately sized subnets using different masks. Think of the pizza analogy from the textbook. Instead of cutting your entire IP address pizza into equal small slices when some departments only need a tiny sliver, VLSM lets you create different-sized slices to match varying departmental needs precisely.
So if one department needs, say, 128 hosts, but another only needs 22.
Exactly. With VLFM, you don't waste a huge block of IPs on the department needing only 22 hosts. You carve out a smaller 27 or 28 for them, and maybe a 25 for the larger department, all from the same original block, like a 24. It's a significant strategic advantage for IP address management, especially in large organizations still heavily reliant on IPv4.
Given that IPv4 is so limited, how does this all translate to IPv6, which has a seemingly infinite address space? Does subnetting even matter there?
IPv6 changes the game quite a bit. Subnets in IPv6 work differently because IPv6 addresses are classless by design right from the start, and they don't use subnet masks in the traditional sense. They rely solely on a prefix length, much like CIDR notation for IPv4. An IPv6 address is typically 128 bits long, composed of a 64-bit network prefix and a 64-bit interface identifier, often derived from the SE address. While you might see them with a slash, like 2608.fe10.1.a64, the standard practice is that the leftmost 64 bits are always the subnet portion.
So a huge subnet by default.
Massive. An organization typically gets assigned a large block, like a 48 or maybe a 56 prefix from their ISP. They then use the bits between their assigned prefix and the 64 boundary for their internal subnetting. This usually gives them between 8 and 16 bits for subnetting, which allows for 65,536 subnets if using 16 bits, an incredibly vast address space compared to IPv4. The management challenge shifts from conserving addresses to simply managing and documenting their sheer abundance logically. But the principle of dividing the network into manageable routable segments remains exactly the same. This fundamentally enhances your understanding of identifying telecommunications fundamentals and designing logical networks for any given set of requirements, regardless of the IP version.
So subnets handle our IP addresses and routing at layer 3. Logical addressing, routing paths. But what about VLANs? They sound similar to subnets sometimes, yet you said they operate on a different layer, right? What's the strategic difference from a business perspective? Why have both?
That's a crucial distinction, and it highlights how network architects use different tools for different jobs. They are definitely not the same thing, though often used together. If subnets are about layer 3 IP addressing and routing, VLANs operate at layer 2, the data link layer. Think Ethernet frames and MICMRUM addresses. VLANs are about logically separating devices on a physical network, effectively creating multiple virtual local area networks, LANs, on the same physical infrastructure, like on a single switch or across multiple connected switches. This directly addresses the problem of excessive broadcasts on large LANs, layer 2 domains, and significantly enhances security without necessarily needing to physically rewire or buy lots more switches.
Okay, so VLANs create virtual boundaries within the physical network at layer 2. How does that compare to a traditional non-VLAN setup?
Right. In a traditional LAN, all devices connected to a single switch are part of the same broadcast domain. This means broadcasts from any device reach all other devices on that switch. As a network grows, this broadcast storm, just constant chatter, can lead to significant performance degradation, everyone shouting, nobody can get work done efficiently. A VLAN, or virtual local area network, solves this. It logically segments a layer 2 network, for example, a single physical switch, into multiple isolated broadcast domains. Traffic within VLAN 10 stays in VLAN 10. Traffic in VLAN 20 stays in VLAN 20. They can't hear each other's broadcasts.
Even if they're plugged into the same physical switch.
Even if they're plugged into the very same physical switch, this restricts access and limits unnecessary traffic flow. Historically, before VLANs became common, achieving this kind of network isolation required entirely separate physical hardware, separate switches, separate cabling for each isolated network segment. Imagine the cost and complexity for a business needing to separate, say, 5 departments. VLANs changed all that.
So, if a growing company wants to keep hardware costs down, but still needs to logically separate its departments for security or performance, VLANs are a definite game changer. What are the key business advantages that make them so popular?
Absolutely, they're a massive strategic advantage for exactly those reasons. Let's list some key benefits. Enhanced security is a major one. By creating distinct Layer 2 security boundaries between groups of users or departments, you can prevent direct communication between, say, accounting and sales traffic at the switch level. Traffic has to go up to a router, Layer 3, to potentially cross between them, where you can apply firewall rules. This provides a critical layer of defense.
Stopping snooping within the same switch.
Precisely. It also leads to cost reduction, because you don't need loads of additional physical switches or routers just for segmentation. One physical switch can host multiple virtual networks, optimizing your hardware investment significantly. Then, there's flexible grouping. Users can be members of a VLAN irrespective of their physical location on the network. A finance team member plugged in on the first floor can be on the same secure VLAN as a colleague plugged in on the 10th floor, facilitating collaboration while maintaining that crucial security boundary.
And performance for critical stuff.
Yes, for critical services, VLANs allow for priority handling. You can configure quality of service QoS settings based on VLANs, ensuring applications like voice over IP get the bandwidth and priority they need for clear calls, directly impacting customer satisfaction and operational efficiency. Traffic isolation for things like VoIP or maybe heavy video streaming is another big plus, and they make setting up temporary networks for projects much easier.
So are there different kinds of VLANs for different purposes beyond just segregating departments like sales and accounting?
Yes, very much so. Network designers use several types. There's a default VLAN, usually VLAN 1. By default, all ports on a managed switch belong to this VLAN initially. It's generally recommended not to use VLAN 1 for user traffic for security reasons. A data VLAN is your standard VLAN for regular user-generated data traffic, web browsing, email, file access, etc. Most user ports will be assigned to a data VLAN. A voice VLAN is specifically configured for IP phone traffic. Switches can often identify voice traffic and automatically place it in this VLAN, prioritizing it to ensure quality of service, QoS, for clear, uninterrupted calls. A management VLAN provides a secure, dedicated channel for network administrators to manage the network devices themselves, switches, routers, firewalls, via protocols like SNMP, SSH, or Telnet. This isolates sensitive administrative traffic from regular user traffic. And the native VLAN is a concept related to trunk links. We'll get to those. It's the one VLAN whose traffic crosses a trunk without an 802.1q tag. It's often used for backward compatibility or control traffic, but like the default VLAN, using VLAN 1 as the native VLAN is often discouraged for security. Each type serves a specific function to optimize and secure the network based on traffic needs.
How do devices actually get assigned to these different VLANs? Is it manual or automatic?
Good question. There are three primary methods for VLAN membership assignment. Port-based VLAN assignment, also called static VLANs, is the simplest and most common. You, the administrator, statically assign a specific VLAN ID to a physical switch port. Any device plugged into that port automatically becomes part of that VLAN. Simple, secure, but less flexible if users move around a lot. MAC address-based VLAN assignment, or dynamic VLANs, is more flexible. The switch maintains a table mapping device MAC addresses to specific VLAN IDs. When a device connects, the switch checks its MAC address and dynamically assigns it to the correct VLAN, regardless of which port it plugs into. This is great for mobile users or environments where devices frequently change physical locations, ensuring they always land in the correct secure segment.
More complex to manage at that table, though.
A bit more complex up front, yes. Lastly, protocol-based VLAN assignment allocates VLAN membership based on the network protocol being used in the frame, like IP, IPX, or AppleTalk, though IP is dominant now. This can help optimize traffic flow or apply specific policies based on the type of traffic, like automatically putting all VoKey traffic into the voice VLAN based on its protocol characteristics. This ability to select and configure devices efficiently is key.
Okay, so if a VLAN is about segmenting a physical switch, how do they work across multiple switches? You mentioned a finance person on floor 1 and floor 10 being in the same VLAN. How does that traffic cross between switches while staying in its VLAN?
That's the real power and scalability of VLANs. They absolutely transcend individual switches. This allows a single logical VLAN, like the finance VLAN, to function across an entire campus-wide network, spanning dozens or even hundreds of switches, not just on one box. This is achieved through what we call trunk ports, or trunking. A trunk port is a special type of switch port configured to carry traffic from multiple VLANs simultaneously between network devices, usually switch to switch or switch to router. Think of it as a multi-lane highway for VLANs.
How does the next switch know which which VLAN the traffic belongs to?
The magic happens thanks to the IE 802.1q standard. This is the universal standard for VLAN tagging. When an Ethernet frame from, say, the finance VLAN, let's call it VLAN 10, needs to leave a switch via a trunk port to go to another switch, the first switch inserts a small tag, the 802.1q tag, into the Ethernet frame header. This tag contains the VLAN ID, in this case 10. The next switch receiving the frame over the trunk link reads that tag, sees it belongs to VLAN 10, and knows only to forward that frame out of ports that are also members of VLAN 10 or another trunk port. The tag is usually removed before the frame is sent out of a regular access port towards an end device.
So the tag directs the traffic correctly across the multi-switch network.
Exactly. It efficiently extends that logical segmentation across your entire network infrastructure without needing tons of redundant cables for each individual VLAN between switches. This saves significant wiring complexity, port usage, and ultimately cost for the business.
Can you give us a really concrete, real-world example where VLANs are absolutely essential, especially hitting on that security and performance aspect for a business?
A perfect everyday example is Voice over IP, or VoIP. VoIP phones are essentially specialized computers running on your network. From a security perspective, just plugging a phone into your standard data network and sending voice conversations as unencrypted data packets is a terrible idea. Tools like Wireshark, which capture network traffic, can easily sniff those packets, reassemble the conversation, and potentially convert them back to audio files. Imagine someone listening in on confidential client calls or internal strategy discussions.
Oof. Yeah, not good.
Not good at all. What's more, to save on cabling costs, VoIP phones often have a second port on the back to daisy-chain a user's computer. This means regular computer traffic, browsing, email file shares, and sensitive voice data are physically intermingled on the same switch port and potentially the same network segment if not properly configured. This creates both those security risks and potential performance issues. A large file transfer could make your phone call choppy.
So what's the VLAN solution?
The standard best practice solution is to deploy VoIP phones on their own dedicated voice VLAN, separate from the data VLAN used by computers. This completely isolates the voice traffic. From a security standpoint, computers on the data VLAN generally cannot see or touch the phone's network traffic, preventing eavesdropping or attacks originating from a compromised PC. From a performance perspective, all the computer data traffic, file transfers, web browsing, etc., will never impact the quality or reliability of the phone conversations because they're in separate broadcast domains and can be prioritized differently using QoS. It's a clean, secure, and high-performance solution that directly protects critical business communication and customer service.
That's a very clear illustration of immediate business value right there. But even with all these benefits, segmentation, security, performance, are there still security concerns we need to be aware of when using VLANs, or are they pretty much foolproof once set up?
No technology is ever truly foolproof, unfortunately. While VLANs are inherently much more secure than traditional flatlans, misconfigurations or vulnerabilities in switch software can still be exploited by determined attackers. One major concern is VLAN hopping. This is where attackers use techniques to send packets to VLANs they shouldn't have access to. Common methods include double tagging, inserting two VLAN tags to trick switches, or switch spoofing, tricking a switch into thinking the attacker's machine is another switch, thus allowing it to negotiate a trunk link.
Sneaky. What else?
Another potential issue is inter-VAN routing issues. Remember, for VLANs to talk to each other, traffic has to go through a Layer 3 device, router or Layer 3 switch. If the access control lists, ACLs, or firewall rules on that routing device aren't properly configured and restrictive, sensitive data could still be exposed to unauthorized users hopping between VLANs at the routing point. And while VLANs reduce the scope of broadcast storms, misconfigurations, like loops, within a VLAN can still cause significant network degradation for all devices in that specific VLAN.
So how do we defend against these? What are the key mitigation strategies?
Good network hygiene and following best practices are paramount. Don't use the default VLAN, VLAN 1, for any user or sensitive data traffic. Assign all ports to other specific VLANs. Change the native VLAN on trunk ports to an unused VLAN ID, not VLAN 1. Disable auto-trunking protocols, like Cisco's DDP, on user-facing ports. Manually configure ports as either access for end devices belonging to one VLAN or trunk, carrying multiple tagged VLANs. Don't let them negotiate automatically. When configuring trunk ports, explicitly specify which VLANs are allowed to cross that trunk rather than allowing all VLANs by default. Principle of least privilege. Implement strong access control lists, ACLs, at the Layer 3 boundary, the router Layer 3 switch, to strictly control traffic flow between VLANs. And of course, don't forget physical security for your network closets and equipment. Following these steps diligently is crucial for formulating a robust risk assessment and developing an appropriate security strategy when deploying VLANs. They aren't magic, they require careful configuration.
Managing all those VLANs, manually creating them, assigning ports, ensuring consistency across dozens, maybe hundreds of switches in a large organization sounds like a potential nightmare for a network administrator. Is there a way to automate this process to save time and, importantly, reduce human error?
You've hit on a very real operational challenge that often plagues growing networks. Configuration consistency is key, and manual repetition is prone to mistakes. That's exactly where VLAN trunking protocol, or VTP, comes into play, at least in the Cisco world where it originated. VTP is designed specifically to simplify VLAN management, especially in extensive campus networks with many switches. The idea is, instead of manually creating the same, say, 50 VLANs with the same names and numbers on 20 different switches one by one.
Which sounds tedious and error-prone.
Exactly. You can configure them just once on a central switch designated as a VTP server. VTP then automatically propagates that VLAN information additions, deletions, name changes to all other participating switches in the same VTP domain. This automation can save an enormous amount of time and administrative effort for IT teams, reducing configuration errors and improving overall consistency across the network.
Okay, that sounds useful. How does it work? Are there different roles switches can play in this?
Yes, VTP operates in different modes, and understanding these is critical. The VTP server mode is typically configured on one or maybe two central switches. This is the switch where you, the administrator, actually create, modify, or delete VLANs for the entire domain. It stores the master VLAN information and is responsible for sending out VTP advertisements containing updates. VTP client mode switches listen for these VTP advertisements from servers in the same domain. They automatically synchronize their own VLAN database based on the information received. Importantly, you cannot create, modify, or delete VLANs directly on a VTP client switch. It just learns from the server. But it does forward VTP advertisements. It receives out its trunk ports to other switches. VTP transparent mode is a bit different. Switches in this mode do not participate in the VTP domain synchronization. They will forward VTP advertisements they receive through their trunk ports for other switches, but they ignore the content of those advertisements for their own configuration. A transparent switch can create, modify, and delete VLANs locally, but these local VLAN configurations are only stored locally, usually in the running config, and are not advertised to other switches in the VTP domain. It acts like a VTP pass-through.
So server makes changes, client learns changes, transparent ignores changes but lets them pass through. How does VTP actually ensure all these clients stay in sync correctly? It sounds like it could be a powerful tool for consistency if it works right.
It relies on a few key mechanisms working together. First, all participating switches, servers and clients, must be configured with the same VTP domain name. This acts like a password or administrative boundary, ensuring only switches intended to be part of the same management group synchronize with each other. Second, and absolutely critical, is the revision number. This is a 32-bit counter stored on each switch, server and client, that tracks changes to the VLAN database. Every time a change is made on a VTP server, the revision number on that server increments. When a VTP server sends out an advertisement, it includes its current revision number. VTP clients compare the revision number in the received advertisement to their own stored revision number. If the received number is higher, the client knows the server has newer information and immediately overwrites its own VLAN database with the information from the advertisement, updating its own revision number to match. If the received number is lower or equal, it ignores the advertisement.
Higher revision number wins. Sounds simple enough, maybe too simple. What's the catch? You hinted at risk earlier.
Yes. The higher revision number always wins. And that simple rule is precisely where the critical security risk lies. And this is why many experienced network engineers are extremely wary of VTP, especially older versions. While VTP sounds incredibly useful for automation, that synchronization mechanism based purely on the highest revision number creates a significant vulnerability. Here's the danger. Any switch in the VTP domain, even a VTP client, if it happens to have a higher revision number, perhaps accidentally brought in from a lab environment or due to a past misconfiguration, can potentially overwrite the VLAN database of all other switches in the domain, including the designated VTP servers.
Wait, a client can overwrite the server just by having a bigger number?
Yes, because the protocol dictates that everyone synchronizes to the highest revision number they see advertised within the domain. Imagine this disastrous but entirely possible scenario. You have a stable production network with hundreds of correctly configured VLANs running smoothly, managed by your VTP server with, say, revision number 50. An engineer takes an old switch out of a storage closet. This switch was previously used in a lab, configured as a VTP client in the same domain name, and maybe had hundreds of test VLANs created and deleted, pushing its revision number up to, say, 200. The engineer, unaware of its high revision number, plugs this old switch into your production network via a trunk link. That switch immediately sends out a VTP advertisement announcing its VLAN database, which might be empty or completely wrong for production, with revision number 200. Oh no, it's right. Every other VTP client and server switch on your network sees this advertisement, compares revision 200 to their current 50, sees 200 as higher, and immediately says, New configuration. They then proceed to wipe out their entire correct VLAN database and replace it with the potentially empty database from the rogue switch.
Causing chaos.
Complete chaos. All VLAN definitions across the entire network could vanish instantly. Interfaces assigned to those now non-existent VLANs would likely go inactive or revert to a default state, effectively bringing down large portions, if not all, of your switched network. Phone systems, servers, user connections, everything relying on those VLANs would stop working. It can take hours to recover, manually rebuilding the VLAN database from scratch or backups.
That sounds like a network administrator's absolute worst nightmare and a colossal business disruption. So the practical takeaway is extreme caution with VTP.
Absolutely. Due to this inherent and potentially catastrophic risk, VTP, while efficient in theory, must be managed with extreme caution in practice. Many organizations, especially larger ones or those with strict change control, choose to disable VTP entirely by setting all switches to transparent mode and rely on manual configuration or more modern, safer automation tools like scripting with Python, Ansible, or vendor-specific management platforms. If VTP is used, it's often VTP version 3, which has some safeguards like a primary server concept, or used only in transparent mode for non-server switches, combined with very strict change management processes and never introducing switches without resetting their VTP revision number first. It's a prime example of why formulating a robust risk assessment is so crucial in network management. Convenience can sometimes come with hidden dangers.
Good lesson there. Is there anything else useful about VTP besides the main synchronization?
Yes. One other feature often associated with VTP is VTP pruning. This is actually quite beneficial for network efficiency. Without pruning, by default, broadcast, multicast, and unknown unicast frames for a particular VLAN are flooded across all trunk links in the network, even to switches that have absolutely no torts assigned to that specific VLAN. This wastes valuable bandwidth on those trunk links.
Sending traffic where it doesn't need to go.
Exactly. VTP pruning, which needs to be enabled, intelligently prevents this unnecessary traffic flooding. Switches communicate with each other about which VLANs they actually have active ports for. VTP pruning then ensures that traffic for a specific VLAN is only sent over a trunk link if the switch on the other side actually needs to receive traffic for that VLAN, i.e. has active ports in it. It optimizes bandwidth usage on your critical trunk connections and contributes to more efficient network management.
Okay, pruning sounds good, but the core VTP sync sounds risky. Got it. Now this brings us back to a common point of confusion for many learners, myself included sometimes. We've talked about subnets and VLANs separately, but they often get mixed up or used interchangeably in casual conversation. What's the absolute core difference we need to remember to truly understand segmentation, and how do they interact to build a truly robust and secure network?
That's a fantastic question to clarify because understanding this distinction is fundamental. While both subnets and VLANs are indeed tools for segmenting networks, their fundamental operational layers within the OSI model are the absolute key to understanding their distinct roles and why you typically use both. Think of them as complementary tools in your network architect's toolbox, definitely not interchangeable ones. They work together, hand in hand, to create a robust, layered approach to network isolation and security. One handles layer 2, the other handles layer 3.
Okay, layer 2 versus layer 3. Break down those core conceptual differences again for us.
Let's nail this down. OSI layer of operation. This is the most critical distinction. A VLAN operates at layer 2, the data link layer. It's primarily concerned with Ethernet frames, MAC addresses, and isolating broadcast domains within a switched network. A subnet, on the other hand, operates at layer 3, the network layer. It deals with IP packets, logical IP addresses, and routing between different network segments.
So VLANs group devices that can talk directly via MAC addresses, subnets group devices by IP addresses that need a router to talk between groups.
That's a great way to put it. Primary function. A VLAN's main goal is to logically segment a physical switch network, like a single switch or group of switches, into multiple isolated broadcast domains. It's about creating virtual LANs on shared physical hardware, controlling who hears whose broadcasts. A subnet's primary function is to logically divide a larger IP address space into smaller, distinct routable segments. It's about organizing your IP addressing scheme logically.
Device awareness.
Device awareness. A VLAN operates based on AMSAG, addresses the physical hardware address burned into a device's network card. Switches make forwarding decisions within a VLAN based on MACs. A subnet operates based on IP addresses, the logical address assigned to a device via configuration, or DHCP. Routers make forwarding decisions between subnets based on IP addresses.
And the big one, how do devices in different segments talk to each other?
Inter-segment communication. This is where the layers really show their difference. For devices in different VLANs to communicate, even if they are plugged into the same physical switch, their traffic must go through a Layer 3 routing device, typically a router or a Layer 3 capable switch. The VLAN creates a hard boundary at Layer 2. Simply being on the same physical switch is not enough for different VLANs to talk directly. Communication between devices in different subnets, however, is inherently handled by routing at Layer 3. That's what routers do. They forward packets between different IP subnets based on their routing tables.
Okay, that clarifies it. VLANs isolate at layer 2, subnets organize at layer 3, and you need a router to bridge between them. So if they're different tools, how should they ideally work together in a well-designed, secure network? Is there a best practice?
Precisely. They are different but designed to work together beautifully. In most modern enterprise network designs, there's a fundamental best practice, often referred to informally as the one broadcast domain, one VLAN equals one subnet rule. This means that, by design, each VLAN you create is deliberately assigned its own unique IP subnet. For example, VLAN 10, sales, might use the 192.168.0.024 subnet. VLAN 20, marketing, uses 192.168.024. VLAN 30, servers, uses 10.1.30.024, and so on.
Why is that pairing so important?
This tight pairing provides segmentation benefits at both Layer 2, broadcast containment via VLANs, and Layer 3, IT-based routing control via subnets. It creates a highly robust, clearly defined, layered approach to network isolation and security. It ensures that traffic within a VLAN naturally stays within its assigned IP subnet unless it's explicitly routed by a Layer 3 device. This adds a powerful layer of control and defense, making the network easier to manage, troubleshoot, and secure, which is absolutely vital for any organization today.
How do we technically enable that routing between VLANs when they're mapped to subnets, especially if we want to use powerful switches instead of separate routers?
That's where Layer 3 switches and a feature called Switch Virtual Interfaces, or SVIs, come into play. An SVI is essentially a logical, virtual Layer 3 interface created on a Layer 3 capable switch that represents a specific VLAN within that switch. You create an SVI for a particular VLAN, say interface VLAN 10, and assign it an IP address from the subnet associated with that VLAN, e.g. address 192.168.0.1, 255.255.255.0. This IP address on the SVI then acts as the default gateway for all devices within that VLAN subnet.
So the switch itself becomes the router for its connected VLANs.
Exactly. It allows a single Layer 3 switch to perform high-speed inter-VLAN routing directly in hardware, connecting multiple VLAN subnets together without needing an external dedicated router, often called router on a stick in older setups. This is much faster, more scalable for internal campus traffic. This knowledge is absolutely crucial for understanding modern network infrastructure and being able to design logical networks effectively for any given set of business requirements.
Okay, so we've pretty much mastered on-premise segmentation. We've got our physical hardware cables, switches, routers. We understand subnets at layer 3, VLANs at layer 2, and how they work together using SVIs. But what happens when we move our infrastructure or parts of it to the cloud? Does all this knowledge just, I don't know, disappear? Does segmentation fundamentally change from a business strategy perspective?
That's the million-dollar question, isn't it? And it's where the rubber really meets the road for modern IT infrastructure and strategy. The cloud fundamentally changes how these concepts are implemented and managed, even if the core goals of segmentation, achieving better security, performance, and manageability, remain exactly the same. In the cloud, the underlying physical network, especially the Layer 2 infrastructure, like the actual switches and VLAN tagging mechanisms, is largely abstracted away from you, the customer. The cloud provider, AWS, Azure, GCP, manages all that complex physical stuff. This means you generally don't directly configure things like 802.1q VLAN tags on virtual switches or manage VTP domains like you would on your own physical premises. The provider handles that underlying complexity for you.
So less tinkering with the low-level stuff.
Less tinkering with the low-level Layer 2 stuff, yes. But the need for logical segmentation is arguably even more critical in the cloud. Let's just quickly touch on cloud computing overview again. It's essentially utilizing remote servers and services hosted on the internet, the cloud, to store, manage, and process data, run applications, etc., rather than relying solely on your own local physical hardware in your own data center. The business benefits are well known now. Potentially reduced hardware investments and operational costs, easier scalability, pay for what you use, centralized data storage and backup, often improved disaster recovery capabilities, enhanced collaboration tools, remote access, and perhaps counterintuitively to some initially, often significantly increase security, as major cloud providers invest billions in securing their infrastructure and offer advanced security services that might be unaffordable for individual companies.
Right, that ability to leverage enterprise-grade security tools is huge.
It really is.
Yeah.
The real game changer in the cloud, from a networking and security perspective, isn't just that these segmentation and security services exist, but how they allow even small and medium-sized businesses to deploy world-class, highly secure, enterprise-grade networking architectures relatively easily, leveling the playing field significantly.
Okay, so if we don't directly manage physical switches and VLAN tags in the cloud, how do we achieve that crucial segmentation? How do we carve out our secure zones virtually up there?
Great question. It's about abstraction, not elimination. While you don't typically mess with direct Layer 2 VLAN tagging, like 802.1q, or manage the underlying virtual switch configurations yourself, similar isolation functionality is achieved through cloud-native services and constructs that operate primarily at Layer 3 and Layer 4 network and transport layers. For instance, in Amazon Web Services, AWS, you use security groups. These act like stateful virtual firewalls attached directly to your virtual machine instances, EC2 instances, controlling inbound and outbound traffic based on ports and protocols. You also use network access control lists, NACLs, which are stateless firewalls applied at the subnet level, providing another layer of defense.
And in Azure.
In Microsoft Azure, the equivalent concepts are network security groups, NSGs, which function very similarly to AWS security groups and can be applied to individual virtual machine network interfaces, NICs, or entire subnets. Azure also offers Azure Firewall, a more powerful managed stateful firewall service that can protect your entire virtual network. Google Cloud Platform, GCP, uses firewall rules. These constructs effectively mimic the isolation goal of VLANs by allowing or denying traffic between different logical segments, like subnets or groups of instances, based on defined rules, ensuring your cloud resources are isolated and protected according to your policies.
So if VLANs take a backseat, does that mean subnets become even more important in the cloud?
Absolutely. In the cloud, subnets become the primary method of logical segmentation that you, the customer, directly define and manage. Services like Amazon's Virtual Private Cloud, EPC, and Azure's Virtual Network, VNet, are your foundational customer-managed software-defined network spaces within the cloud provider's infrastructure. They are your private, isolated slice of the cloud. Within these VPCs or VNets, you explicitly define subnets as your primary tool for logically organizing your resources, like virtual machines, databases, load balancers, and applying network policies like routing and security rules. Each subnet you create gets its own IP address range, CIDR block, and typically serves as a distinct routing boundary.
Are there different types of subnets in the cloud, like public versus private?
Yes, that's a very common and important pattern. Using AWS as an example, you'll almost always create private subnets. Resources launched into these subnets, like back-end application servers or database servers, have no direct route to or from the public internet. This significantly enhances security for your sensitive internal systems. Public subnets. Resources here, like web servers or load balancers that need to be internet-facing, can communicate directly with the internet, usually via an internet gateway, IGW, attached to the VPC. Security and traffic flow between these cloud subnets is meticulously controlled using route tables, which define where traffic destined for certain IP ranges should go, and those security rules we just discussed, security groups, NACLs, NSGs, firewall rules. This directly demonstrates how you configure network connections, services, and security for a given set of requirements within a cloud context.
Okay, so the core principles of segmentation using IP ranges and routing remain, just implemented with different virtual tools. What other essential cloud security and access tools are critical to keep these segmented environments both secure and practically usable for a business? We need to get to our private resources somehow, right?
Exactly. Just having private subnets isn't enough if you can't manage them securely. Several other resources are critical for modern cloud security and access. A NAT gateway, Network Address Translation Gateway, is often placed in a public subnet. It provides secure, outbound-only internet connectivity for instances residing in your private subnets. This allows your private servers to, say, download software updates or connect to external APIs without allowing the internet to initiate connections back to them. They don't need public IP addresses themselves.
So they can talk out, but nothing can talk indirectly.
Precisely. For inbound administrative access to those private instances, you typically use a bastion host, also sometimes called a jump box or jump server. This is a specially hardened server, like a Linux or Windows VM, strategically placed in a public subnet. Administrators first connect securely, e.g. via SSH or RDP, to the bastion host, and then from the bastion host, they jump to the private instances. It acts as a secure, controlled gateway, minimizing the attack surface of your private network.
Like a secure airlock.
A great analogy. And some cloud providers offer managed bastion services, like Azure Bastion, which provides secure RDP-SSH connectivity directly through the Azure portal in your web browser without needing to manage the Bastion VM yourself or expose RDP-SSH ports publicly. We're also seeing the rise of services based on zero trust principles, like AWS Verified Access. This service provides secure access to specific applications without needing a traditional VPN connection at all. It evaluates every single access request in real time against specified security requirements, like user identity, device health, location, before granting access, ensuring users only access authorized applications after meeting strict conditions.
So moving beyond network-level access to application-level context-aware access.
Exactly. This highlights a key trend in cloud security. Designing multiple, highly restricted microsegments, often down to the individual application or even function level, with very limited, strictly controlled interconnectivity, even if they technically reside within the same larger virtual network. It's all about enforcing the principle of least privilege everywhere. This thinking is fundamental when selecting appropriate access solutions and configuring secure network connections.
And what about getting content and applications closer to users globally? How does cloud segmentation and network design play into achieving high performance and availability for a business aiming for a global reach?
That's where the concept of cloud at the edge becomes incredibly important, significantly enhancing both performance and availability. Content delivery networks, CDNs, are a prime example. Services like Amazon CloudFront and Azure Front Door work by caching copies of your content static files like images and videos, but also dynamic application responses at numerous edge locations, spread strategically around the globe, physically closer to your end users. When a user requests your content, the CDN automatically serves it from the nearest edge location, drastically reducing latency, the delay in loading, and improving availability. If one region has issues, others can still serve. It also offloads traffic from your origin servers. This is how major websites and streaming services deliver content instantly no matter where you are in the world. For any online business, this directly impacts user experience, conversion rates, and global reach.
So CDNs use segmented edge infrastructure. What about processing data at the edge?
All right, beyond just caching, we have edge computing. This involves actually processing data closer to where it's generated or needed, rather than sending it all back to a central cloud region. This is absolutely critical for applications requiring ultra-low latency, like real-time industrial controls in an IoT setting, autonomous vehicles, augmented reality, or real-time analytics on factory floors. These edge deployments often leverage segmented cloud infrastructure extending out towards the user or device location, sometimes using specialized hardware or services offered by cloud providers like AWS Outposts or Azure Stack. They allow localized processing and connectivity, showcasing how selecting appropriate wireless or wired components and designing logical networks extends right out to the very edge of the cloud.
Given how absolutely critical cloud computing has become for businesses of all sizes, from startups to global enterprises, what are some of the actual specific services that major providers like AWS and Azure offer to implement all this advanced segmentation, security, connectivity, and content delivery in the real world? For our business students listening, what's the strategic value these specific services provide? Why should they know these names?
That's a great way to frame it. What's really fascinating here is how the major cloud providers, especially Amazon Web Services, AWS, and Microsoft Azure, offer an incredibly broad, deep, and integrated suite of networking and content delivery services. These aren't just individual tools, they're often designed to work together seamlessly. These are the concrete building blocks that empower businesses, your future employers, or your own ventures to construct highly reliable, secure, scalable, and performant cloud infrastructures. Knowing what's available directly reflects the course's emphasis on understanding alternatives in hardware, software, and transmission facilities, and critically, how to select and implement comprehensive communication solutions in a modern context.
Okay, let's start with AWS. What are some key services in their networking and content delivery category that students should be aware of?
All right, focusing on some core AWS networking and content delivery services. For foundational networking, we've mentioned Amazon VPC, Virtual Private Cloud. This is truly the cornerstone. It's your logically isolated section of the AWS cloud where you launch your resources. You have complete control over your virtual networking environment, including selecting your own IP address range, creating subnets, configuring route tables, and setting up network gateways like Internet gateways or NAT gateways.
Its strategic value is immense. It gives you a customizable, private, secure slice of AWS that functions much like your own traditional data center network, but with cloud scale and flexibility. It supports both IPv4 and IPv6.
The starting point for almost everything in AWS?
Pretty much. For hybrid connectivity, connecting your existing networks to AWS VPN provides services to establish secure, encrypted connections. This includes site-to-site VPN, securely connecting your on-premises data center or office network to your VPCs over the internet, and client VPN, allowing individual users like remote employees to securely connect to AWS or even back to on-premises resources. For more robust, dedicated hybrid connections, there's AWS Direct Connect. This service allows you to establish a dedicated private network connection directly from your premises, data center, office, co-location facility, straight into AWS, bypassing the public internet entirely. This often results in lower network costs, especially for high data transfer volumes, increased bandwidth throughput, and a much more consistent, reliable network experience compared to internet-based VPNs. For businesses heavily reliant on cloud, this provides a secure, high-performance extension of their network.
What about connecting multiple VPCs together or managing complex routing?
That's where AWS Transit Gateway comes in. As organizations grow in the cloud, they often end up with many VPCs, maybe across different AWS accounts. Connecting them all directly with VPC peering becomes complex and hard to manage, a mesh topology. Transit Gateway acts as a central cloud router, a hub that you connect all your VPCs and even your on-premises networks via VPN or Direct Connect to. It drastically simplifies network management by using a hub-and-spoke model instead of complex point-to-point connections. Essential for scaling networks across many accounts and VPCs cleanly. An AWS Private Link is crucial for security. It provides private connectivity between your VPCs, various AWS services like S3 storage, Lambda functions, and even partner SaaS applications running on AWS without ever exposing your data traffic to the public internet. It keeps all the communication securely on the private Amazon network backbone, simplifying network architecture and enhancing security posture significantly.
Okay, foundational, hybrid, simplifying complexity. What about handling application traffic and performance?
Key services there are. Elastic Load Balancing, ELB. This is fundamental for high availability and fault tolerance. ELB automatically distributes incoming application traffic across multiple targets like multiple EC2 instances, VMs, containers, or even IP addresses spread across one or more availability zones. If one instance fails, ELB stops sending traffic to it and routes users to healthy instances. It offers several types. Application Load Balancer, ALB, operating at Layer 7 HTTPS for flexible application routing. Network Load Balancer, NLB, at Layer 4 TCP/UDP for extreme performance and static IPs. Gateway Load Balancer, GWLB, for deploying third-party virtual network appliances, and the older classic Load Balancer. Choosing the right load balancer is key for application resilience. Amazon CloudFront. As we discussed, this is AWS's fast global content delivery network, CDN. It securely delivers data, videos, applications, and APIs to customers globally with low latency and high transfer speeds by caching content at edge locations worldwide. It integrates tightly with other AWS services, including AWS Shield for DDoS protection. Critical for any web-facing application needing speed and global reach. Amazon Route 53. This is AWS's highly available and scalable cloud domain name system, DNS, web service. It translates human-readable domain names, like www.tarleton.edu, into the numeric IP addresses, like 192.0.2.1 that computers use to connect. But it does much more. It offers domain name registration, DNS health checks, routing traffic away from unhealthy endpoints, and advanced traffic flow policies like latency-based routing, geoproximity routing, or weighted routing for A/B testing. It's the reliable phone book for your internet applications.
AWS even has private 5G.
Yeah, relatively new, AWS Private 5G. It offers businesses an easy way to deploy and manage their own private cellular network using 5G or 4G LTE technology on their premises. AWS provides the necessary hardware, SIM cards, small cell radio units, and software. This is aimed at specific use cases needing reliable, low-latency wireless connectivity over a dedicated network, like factory automation, warehouse robotics, or large campus environments where Wi-Fi might have limitations. It's about augmenting existing networks with dedicated cellular tech.
That's a really comprehensive suite from AWS. How does Azure, the other major cloud player, approach these same networking challenges? What are its key offerings that businesses and students should recognize?
Azure offers a similarly robust and comprehensive set of services, often with analogous functions, but sometimes with different names or slightly different approaches. Let's look at some key Azure networking services. For the networking foundation, the core building block is Azure Virtual Network, VNet, Azure's equivalent to AWS VPC. It's your private network space in Azure,
where you deploy Azure resources like virtual machines, VMs. You define your IP address space, create subnets, control routing, and can connect VNets together using VNet peering or connect back to on-premises networks. Security is primarily handled by network security groups, NSGs, which function like stateful firewalls for VMs and subnets, very similar to AWS security groups. For secure access to Azure Platform Services, there's Azure Private Link, similar to AWS Private Link. It allows you to access Azure PaaS services, like Azure Storage, Azure SQL Database, and partner services securely over a private endpoint within your VNet, keeping traffic on the Microsoft Global Backbone Network, never traversing the public internet. DNS is handled by Azure DNS, which provides hosting for public domains, private DNS zones for use within your VNets, allowing you to use custom domain names for your internal resources, and a private resolver service for enabling name resolution between on-premises and Azure. And for secure administrative access, Azure Bastion is the managed CompTIA service we mentioned, providing secure RDP-SSH connectivity to your VMs directly from the Azure portal over TLS, eliminating the need for public IP addresses on the VMs themselves for management.
How about load balancing and content delivery in Azure?
Load balancing and content delivery. Azure offers several options here. Azure Load Balancer is a high-performance, ultra-low latency Layer 4 (TCP/UDP) load balancer suitable for managing both inbound and outbound connections for applications needing raw network performance. For web applications needing more advanced features, Azure Application Gateway acts as a web traffic load balancer or application delivery controller (ADC). It operates at Layer 7 HTTPS and offers capabilities like SSL/TLS termination, cookie-based session affinity, URL path-based routing, and integration with Azure Web Application Firewall, WAF. Azure Front Door is Azure's modern cloud CDN and global load balancing service. Similar in function to AWS CloudFront combined with some Route 53 traffic management features. It optimizes global routing for your web traffic, ensuring users connect to the best, lowest latency, highest availability backend application endpoint. Provides features like instant global failover, path-based routing, SSL offloading, and also integrates with Azure Way for security at the edge.
And connecting back to on-premises networks, Azure's hybrid options.
Hybrid connectivity. Azure offers VPN Gateway, which allows you to create encrypted cross-premises connections to your VNet from your on-premises locations using site-to-site VPNs, or for individual users, point-to-site VPNs, similar to AWS VPN. For higher bandwidth, more reliable private connections, Azure ExpressRoute is the equivalent of AWS Direct Connect. It extends your on-premises networks into the Microsoft Cloud over a private, dedicated connection facilitated by a connectivity partner, completely bypassing the public internet. Azure also has Azure Virtual WAN, which is a networking service designed to simplify large-scale branch connectivity. It consolidates many networking, security, and routing functionalities, like managing VPN, ExpressRoute, VNet to VNet connectivity, and routing policies into a single operational interface, often using a managed hub-and-spoke architecture.
Finally, network security-specific services in Azure.
Network security. Beyond NSGs, Azure Firewall is a managed cloud-native intelligent network firewall security service that provides threat protection for your cloud workloads running in Azure. It offers features like stateful firewalling, built-in high availability, and integration with Azure Monitor for logging and analytics. You deploy it centrally in your VNet or virtual WAN hub. Azure Web Application Firewall, WAF, provides centralized protection for your web applications against common exploits and vulnerabilities like SQL injection or cross-site scripting, often targeting the OWASP top 10. It uses managed role sets and allows custom rules. WAF can be deployed with Azure Application Gateway, Azure Front Door, or Azure CDN. And Azure DDoS protection provides countermeasures against sophisticated distributed denial of service, DDoS threats that can overwhelm applications with traffic. It offers enhanced mitigation capabilities beyond the basic infrastructure protection, tailored for Azure resources deployed in virtual networks.
Wow. Both AWS and Azure offer an incredible depth of services for building and securing networks in the cloud. It really underscores how businesses can now architect sophisticated, scalable, and secure global infrastructures with unprecedented flexibility, moving far beyond just basic servers and storage. It truly embodies how we need to select and configure network connections, services, security, and management for modern requirements.
Exactly. And understanding these specific services, even at a high level, is becoming increasingly important for anyone involved in IT strategy or implementation.
This massive cloud shift sounds truly monumental. It feels like the ground is constantly shifting under IT. What does all this mean for anyone aspiring to a career in networking and IT? Especially thinking about our business students who need to understand the strategic implications of technology, not just the technical details.
That's the perfect question to ask as we bring this together. If we connect this to the bigger picture, the rise of cloud computing isn't just another technological change. It's a profound transformation of the entire IT landscape and how businesses operate. For network technicians, system administrators, security professionals, and absolutely for business leaders and managers as well, it means embracing lifelong learning is no longer optional. It's essential. You have to constantly adapt your skill sets to stay relevant and strategic in your careers. It's really about moving beyond just fixing physical hardware issues, plugging in cables, replacing failed switches to designing, deploying, managing, and securing complex virtualized environments and sophisticated cloud services. It's about becoming an architect of digital strategy, not just a maintainer of physical boxes.
So the role itself is evolving significantly. What does that look like in practice for a network technician today versus maybe 10 years ago?
The role of the network technician is truly transforming. We're seeing a definite, undeniable shift from managing purely physical servers, routers, and bundles of cables to mastering virtual machines, VMs, software-defined networks, SDN, and cloud platforms like AWS, Azure, and GCP. This means an expanded skill set is absolutely critical for success. Your traditional networking knowledge understanding TCP/IP, Ethernet, routing protocols like OSPF, and crucially the subnetting and VLAN concepts we've discussed today that remains foundational. You still need that bedrock. But several new areas are now essential.
Like what specifically?
Virtualization technologies. You need solid proficiency in creating and managing VMs, configuring virtual networks within hypervisors like VMware vSphere or Microsoft Hyper-V, and understanding virtual switches, vSwitches. Cloud networking expertise. This is huge. You need a deep understanding of cloud-specific concepts like virtual private clouds, VPCs, and virtual networks, VNets, elastic IP addresses, cloud load balancers, ELB, ALB, Azure load balancer, security groups, NACL, SNSGs, internet gateways, NAT gateways, VPN gateways, and how they all interconnect. This is fundamental for designing logical networks, specifically for cloud deployments.
So knowing the cloud provider-specific tools is key.
Absolutely. And knowing how they differ slightly. Software-defined networking, SDN. At least familiarity with SDN concepts is becoming vital. Understanding SDN controllers, network virtualization overlays like VXLAN, and the basics of network programmability allows you to leverage the automation and optimization capabilities inherent in cloud networks. It's moving from manual CLI and configuration towards managing networks as code. Cloud security best practices. This cannot be overstated. You need in-depth knowledge of identity and access management, IAM, in the cloud, encryption techniques, data at rest and data in transit, designing secure network architectures using public-private subnets and security zones, configuring web application firewalls, WAFs, and implementing effective network segmentation within the cloud environment using the tools we discussed. Security is job zero in the cloud, and it's integrated everywhere. This directly impacts a company's ability to formulate a robust security strategy.
What about automation and managing hybrid setups?
Automation and orchestration. These are massive trends. Learning to leverage tools like Ansible, Terraform, Chef, Puppet, or even just scripting with Python libraries, like Boto 3 for AWS or Azure SDKs, to automate routine network configuration, deployment monitoring, and troubleshooting tasks is becoming invaluable. It reduces manual effort, minimizes human error, ensures consistency, and frees up engineers for higher-level tasks, all direct benefits to the business. Hybrid network environments. Very few organizations are 100% cloud or 100% on-premises anymore. The ability to seamlessly integrate and manage both environments is crucial. This includes expertise in configuring and troubleshooting VPN connections, direct connect express route links, and ensuring secure and efficient data transfer between your data centers and the cloud. And naturally, advanced monitoring and troubleshooting skills need to adapt. You need to learn how to use cloud-native monitoring tools like AWS CloudWatch, Azure Monitor, and adapt troubleshooting techniques for distributed, often ephemeral cloud environments to identify and resolve performance bottlenecks or connectivity issues quickly, ensuring operational efficiency.
It sounds like a lot more skills are needed now.
It is, but it's also more interesting. This all boils down to adaptability and continuous learning. Cloud computing platforms and services evolve at an incredible pace. Staying updated with industry trends, pursuing relevant industry certifications like the CompTIA network, plus you're studying for, which provides a great vendor-neutral foundation, but then potentially specializing with AWS Certified Advanced Networking, Cisco CCNP Cloud Enterprise, or Azure Network Engineer Associate Expert, and actively participating in professional communities, online forums, user groups, are all absolutely vital for sustained career growth in this field. This curriculum is explicitly designed to prepare you for these industry standard certifications and set you on that path of lifelong learning.
And for the business students listening, Why is this technical evolution important for them?
That's a critical point. For our business students, understanding these fundamental shifts in networking and cloud technology isn't just something the IT department handles. You absolutely must grasp these concepts, at least strategically, to make informed decisions for your organizations. Whether you're in finance, marketing, operations, or management, technology underpins everything. Understanding cloud networking and security allows you to contribute meaningfully to discussions about technology investments, assess operational efficiency gains, understand and mitigate cybersecurity risks, which are now major business risks, and lead effectively during digital transformation initiatives. It empowers you to speak the language of IT, ask the right, probing questions of your technical teams, evaluate vendor proposals intelligently, and ultimately lead more effectively in today's undeniably cloud-centric business world. Ultimately, it's about preparing you to develop professional network proposals that address real business problems using modern solutions, and inspiring you to embrace that lifelong learning necessary for success.
Wow, what a deep dive into the foundational and really cutting-edge world of network segmentation. We started way back at the beginning, understanding why dividing our networks is so vital for security, for performance, for manageability, from simple physical boundaries to complex logical zones for critical things like operational technology and storage area networks, protecting both data and sometimes physical operations.
And we really explored those fundamental distinctions, didn't we? Between subnets, which carve out our IP address spaces at layer 3 for routing, and VLANs, which logically separate broadcast domains down at layer 2 within our switches. We also saw how powerful protocols like VTP, aimed to centralize VLAN management, but how they also carry significant risks if not handled with extreme care, a good lesson in unintended consequences.
Definitely.
And finally, we navigated the shift to the cloud. We saw how services like AWS VPCs and Azure VNets, alongside crucial tools like security groups, NACLs, and NSGs, have become the new foundation for building secure and massively scalable infrastructure, requiring a whole new, yet often complementary skill set focused on abstraction and automation.
It's clear this knowledge isn't just theoretical textbook stuff. It's directly applicable to designing, building, and securing robust business networks in the real world. Ensuring that from the local campus network right up to the global cloud, your data communications are optimized, kept safe, flowing efficiently, and managed reliably. It really is what positions you, our listeners, for success in this rapidly evolving tech landscape, making you a vital asset to any organization you join or build. Ultimately, as we said at the start, it all boils down to creating those smart, secure, and efficient digital highways that ensure data reaches its destination reliably, whether that's just across a small office, throughout a sprawling university campus, or literally around the globe via the cloud. Thank you so much for joining us on this deep dive into network segmentation. If you enjoyed this conversation and found it valuable for your studies or your career planning, please take just a moment to like, subscribe, and maybe share it with a colleague or classmate. Your support really helps us continue bringing you these valuable insights. And don't forget to check the description below for those additional resources we mentioned, links to guides, further reading to help you continue your learning journey and really own your career growth.
And remember, strong connections aren't just technical, they're strategic. Until next time, keep your packets clean and your networks resilient.